So my research topic is now non-reflecting boundary conditions for time-dependent wave propagation. So I studied the wave propagation during my master series and my PhD series, and now also I study also still in this area. So now I'm in the new institute, so Mathematics Institute of Computational Science Engineering. So that is interdisciplinary department in EPFL. So that is my outline. First, I will show you what is wave propagation. So I will introduce this area. And second, I will show you what perfectly matched layers. And third, multiple scattering problems. And first, concluding remarks. Okay, first introduction. So I have here as a nice picture. You can see here easily it's a Titanic below the water. So how can you detect this kind of ship? So perhaps you can go to swimming, or you can send some kind of waves. For example, we can send easily acoustic waves, and then you have any sensor on the water or in the ship, then we can obtain the reflective waves, so that we can recognize this kind of ships. So there are many kinds of methods. First, if you don't know what this is, for example, this is the inverse problem. So we know this shape, so we know this material coefficients and so on, so that we can detect easily with the reflective waves. Second one is metamaterials. So there is a very interesting topic in nanoscience. Also, I worked in Berlin 2004 and 5. So you can see here easily periodic structures here. You can find here the size 15 nanometers. So it's very difficult. It's nanoscale, but if you calculate this one, it's a very long time. So you can imagine it's very. So we have to have any very small discrete points, and then we have to calculate, for example, in this kind of area, so electromagnetic fields, for example. So you have any kind of sources as currents, and then electromagnetic fields propagate inside of this material. So I will show you what it is later, just a motivation. Pardon? There is metamaterials. Oh, okay. There is not metal. Metamaterial means, for example, you can find any kind of material in the nature, but human beings, they want to have any new materials, for example, for making semiconductors or antenna and so on. So there is some kind of materials which made by human beings. Okay, so that we say meta. Meta is some kind of artificial things. Okay. Okay, I can here classify three different wave propagation model problems. So first, wave equation. That is a very standard classical wave equations. So with this equation, we can find any kind of solutions. For example, acoustic pressure in the wave propagation, or also we can also detect some kind of electromagnetic fields also. Second one, Maxwell's equations. So I showed also already in the metamaterials. You can find some kind of numerical solution or exact solution. This one is electromagnetic fields. So we use very often this kind of solution, for example, for mobile phone or television or semiconductor and so on. The third one is elastodynamic equations. For example, football. You can imagine football. You can toss the football, then you have any displacement. But this kind of displacement, you can also calculate it. So the displacement is the solution of elastodynamic equations. In my talk, I would introduce these three different equations. First, wave equation, it looks like this. So first, you have here second derivatives in time, and C is the wave speed. So with the wave speed, you can represent the speed of the wave. How fast can the wave propagate? And the right-hand side, you can see here any kind of force. We have any source term. And this equation is time-dependent problems, so that we have here 0 and t. So 0 is initial time, and big T is maximum time. Omega is a spatial domain. So in 2D, you have a 2-dimension, 3D, 3-dimension. And you need also initial conditions. But I won't put here the boundary conditions. So the reason is that, for example, you have any kind of obstacles. So you can send here the waves. So right? Sorry. Yes. Okay, fine. Okay, if you send here waves, then the wave propagates, right? The problem is, in general, you don't know exactly what the boundary condition is, right? So if the domain is open, right? For example, you can find easily the cross domain. So I like singing a song in the toilet, for example. I can feel very nice. The domain is closed, right? Then you can see, hear very often the reflected waves. So some kind of resonances. This one is closed form, as a closed domain. But in general, for example, if the bell in the church rings, right, then you cannot truncate the computational domain. Its domain is too large, right? So that we need any kind of boundary conditions. So that that is my topic. So I will explain later. So just you can imagine it just initial condition, right? Okay, fine. So second one is somehow complicated equations. This Maxwell equations. This is relatively new equations. You can see that James Clerk Maxwell, 1831, 1879. He lived there in Edinburgh in Scotland. So you can find electric field and magnetic field through these equations. So I will first introduce these two symbols. So I mean curl means in the vectorial calculus you can imagine it just like nabula times, and divergence I can here define as nabula time. Okay. So that is just definition. So E is the electric field, H is magnetic field, and B is magnetic induction. So magnetic induction, you can have any good relationship with the mu. Mu is permeability. So this one is a linear relationship. So we can define linear material laws with this one. H is magnetic field, is the electric displacement, and J is some kind of source term. And sigma, you can also see any kind of relationship J with E. You can see here, J is sigma. Sigma is conductivity times energies. So conductivity you can see very often in the kitchen. So if you want to take any kind of, for example, noodle, you have to cook. Yeah, there exists some kind of conductivity. So that if you have a free source, free domain, you have sigma is 0. You don't have any more conductivity. Okay. Fine. So you have also divergence D is equals rho. Rho is current density. Current density is 0 in a vacuum. Otherwise, it is non-zero. Okay. That is Maxwell's equations. But in general, in the industrial area, the people have interest to find electric field and magnetic field. So that if you have solution of E and H, you can also find D, B, and J. Right. So next one is elastodynamic equations. It has also second derivative in time. Rho is mass density, and minus divergence sigma equals F. Solution of the U is also vectorial because you have, for example, 3 different displacements in space. For example, X direction, Y, and Z direction, and you have also initial conditions. And the stress tensor you can determine with the strain tensor with this equation. And you have also very famous Hooke's law. So stress tensor is related to with matrix C and strain tensor. So that is elastodynamic equations. So perhaps you can understand much better. So I can here repeat with the pictures. So I have here instant waves, and my domain is unbounded, right? So unbounded domain in 2D or 3D, instant wave is a well-known solution, so you can have it already. And total solution, UT. I mean total solution means you can see that if you send the waves as incident waves, then you obtain reflected waves. So that we can determine here total waves is equal to incident wave plus scatter waves. So incident wave is well-known, so that our unknown variables is scattered waves. So that you can have any kind of source near to this area or some inhomogeneous wave speed and so on. So as I said, problem is to have any kind of boundary conditions. So for numerical calculation is very important. You can calculate, for example, 1 year long and so on. So that we have to focus on some interested area. For example, I have just interested in just in this area, for example. And then you can put some kind of boundary condition on the circle. So that we say this special boundary condition is artificial boundary condition. So, inside of this domain, we say the computational domain.
What does the boundary condition mean? You put the detector in some areas. You check that this way.
Yes, somehow.
That gives you the boundary condition.
Yeah, intuitively, right. Intuitively. But we need not the physical formulation, but the mathematical formulation. So I would introduce this boundary condition. Your question is very essential in my talk. Okay. So I would show you with the movie, so you can see. So first, very nicely, intuitively. So you have any exact solution, wave propagates. You know already boundary condition, right? So wave propagates. Fine. And numerical solution, you can see easily. You obtain numerical reflective solutions. Right? So that is not wished solution. So that we don't have any just like reflective waves. So we have to eliminate this kind of reflective waves. That is our destination. So problem is the numerical solution is not exactly in this kind of a formulation. So I will show you first there are various methods to detect these boundary conditions. First, I would introduce perfectly matched layers. For example, our interested domain is here green one, so we have here rectangular, and surrounded this rectangular, we have perfectly matched layers. It looks like just like a bumper, right? So with these perfectly matched layers, the waves are damped. So I will show you here with the solution. So I have here some kind of source point, and then the wave propagates to all directions. I have here the time levels, and then time propagates outside. And then you can see that in here PML layers, we say perfectly matched layers, and then the waves are observed. So that we can here put outside of the domain, we can give any kind of solution. This is zero solutions, right? So the waves are damped. So that destination is we don't have any big numerical reflections. Anyway, right? Yeah.
You mentioned you must have the counterpart.
Yes.
So which one?
Counterpart is that. Here is a white box. So that you have to find any good formulation smoothly. You have to go, the wave propagates, and you don't have any discontinuity, right? So that we say, this layer is perfectly matched layers because of the white box, for example, in 3D.
And the layer is independent of time variable frequency?
Yes, exactly. So yes, exactly. So if you have a high frequency, you have to have any strong dampings, or you have to have a larger the bumper layers. Right.
So it depends on the time.
Depends. You can, yeah, exactly. For example, the wave propagates, and then you have to bump. So you can see that here you don't have any solutions. You don't need two bumps, right? The problem is if you have many kind of sources in the domain, you don't know exactly when such kind of waves reach in the domain. So that a priori we put these observing boundary layers in initial time already. So there are many kinds of methods, but for numerical methods, we have to have any very easily computing, right? We have to have a very simple calculation, but you can also naturally have any complicated analysis. But our destination is to calculate very efficiently and stably. That is our goal. So now we have here the wave equations. So the idea is we can here apply the Laplace transformation in time with the initial values, for example, and no sources in initial time. And then we have here Laplace transformed Helmholtz equations. So if you take here S equals I times omega, omega is frequency, it is just like Fourier transformation, right? So this Laplace transformation we can determine here with the dual variable, we say some kind of scalar variables and times. For example, if you put here S equals complex number, I times omega, then the wave are damped. So with this one. So for the damping profiles, we define any kind of new variables with this one. So perhaps you can think much better in one dimension. For example, the wave propagates. So we put here the observing boundary layers, for example. So our computational domain is just here, omega. And then you can put here the PML layers, then the wave propagates, and then damped. So we define here the PML layers. For example, you can also put here the left-hand side also. That is analog. And your solution is there, so you can put here the new variables. But this new variable is coordinates, right? So this one is x coordinates. And then in the end, we obtain, if you see in the frequency domain, you can see that there is complexified variables. So here you can put new variables. Then the new variables looks like this. So that just in this slide, you can see that there is complex numbers, right? So that, for example, why it is complex numbers? If you put S equals I times omega, I is imaginary part. So you can see that it's very easily the complexified new variables. Okay, if you put this one, then you obtain the new derivatives, also partial derivatives in each coordinate. For example, x1, x2, and x3. Then you can find here a new coordinate system. Okay, so also this for this new coordinate system, we need to have any kind of damping polynomials. So as your questions, we don't have any discontinuity. You have to find any, so continuously we can have here, for example, you can put here this kind of polynomial. That means in computational domain we have here this polynomial is 0, right? So that is non-zero just in the PML layers. So you can control theta 0 with the reflection coefficients. So you can a priori put, for example, I want to have just the reflection coefficient 10 power minus 3, then you can put just this one. And in the question of Professor Lim, the size of the layer you can put also. And it is dependent on also the wave speed. So that you can put these parameters here, and then you can control also here with the layer of the PML. So I show you just my results. So the new PML system for wave equation, as a quote, is my colleague in Basel, and he was my PhD supervisor. And here is you obtain here based on the wave equation. So blue one is the given wave equation, and then black one is new terms for PML layers. And you can find here the auxiliary variables phi and psi. And p and psi you can also determine based on this solution u and u. So that means if you calculate in time domain, you update your solution in each time step. That means this u and phi and psi is old variables. So there is old solutions. And then you calculate the new solution based on this derivative and psi. And then you calculate here. You can put just the right-hand side of this equation. That means phi and psi is old variables. So that it looks like just the right-hand side in the wave equations. This is very simple. And you can see here also the
PML is the artificial layer to have better performance in the numerical.
Yes, exactly. Yes.
And how would it help? I mean, I couldn't understand why you put that part in the numerical.
Yes, yes. I will show you. So, right. For example, you can imagine it much better in the frequency domain, right? For example, I give here the given wave equation. So it's better to understand in one dimension. So I just introduce you in one dimension. So if you put here, for example, Fourier transformation in time, transformation in time t, then we obtain the following equations. That means 1 over c square, and then you have here the new variables minus omega square. You had minus d square dx square equals 0. So The reason is that if you put the Fourier transformation in time, the time derivatives, time derivatives equals to I times omega and so on. So, right, you can just change the time derivative I times omega. And then you have the Fourier transformation, right? So that is exactly, so we can put it, and then we can see that. So del square u and dx square plus omega by c square, that means wave number. Right? So that you can find the solution here. The solution, you can see that solution is that you can see here either two components of the solution. You can find here, for example, alpha 1 exponential function minus ikx plus alpha 2 exponential function ikx. Right? So you can assume this one is, it goes to right hand side, the wave propagates, and then this one it propagates to left hand side. And then you can see that here, the problem is if you put here the absolute value of the solution in each terms, it is just 1, right? But if you we can determine this one, for example, we determine this one u1, we define this one u1, and this one is for example u2, and then you can see here, nice, okay, but I put here, so u2, that is the solution which represent the propagation to right hand side. Yeah. So you have here the solution. So for example, alpha 2 exponential function ikx. The problem is you have two unknowns. In this case, alpha 2 is unknowns, right? So that on the boundary you don't have any kind of boundary conditions. But if you put a change of the variable, for example, x goes to x tilde, for example, you can see that some kind of, for example, x1 tilde. So x1 tilde is just, I put x1 plus I sigma x1. That means I have some kind of damping parameters, I sigma and x1. So if you put sigma is 0, that is just a given coordinate system, but sigma is non-zero in the PML layers, right? That means u2 with this one, you can determine here u2 is equals to alpha 2 exponential function. So I write also the transformed solution so that you can put it ikx. So instead of x, we have x tilde. So x tilde means 1 plus I sigma and x1. And then if you calculate this one, for example, you can obtain ik x1 times. So you see, I times I is minus 1, so that you have here minus k sigma x1. So if you put this one on the boundary, you can see that if you have the positive sigma, then the wave amplitude would be smaller and smaller. So that is the idea of the PML, right? So that is the correct answer to you. So
this guy, yes,
yeah.
he is worried about what's going on the outer layer,
Yeah.
inside of layer, inside
Yeah.
matching. What does it mean?
Yeah. Okay. Okay. So then this good things. So that if you see that in 2D case, for example, in 2D case, so you have two coordinate systems, sigma 1 and sigma 2, and the problem is here. You have here the corner regions, because you have here x1 and x2 coordinates, then two coordinates meet in this area. That means in this area you have the damping parameter sigma 1, as for example sigma 2 is non-zero, but in this one is sigma 1 is non-zero, but sigma 2 is 0. So just like this you can formulate, but in the end, outside of the PML layer you can put zero boundary conditions. You can put, because sigma is very large, for example, then the solution of U2 on the boundary in the PML layer is very small. So, right? You can control this one with the damping parameters, or you can enlarge your computational domain for PML layers. Okay. So that is as a new wave equation for PML. If you have this equation, you can calculate in unbounded domain all kind of acoustic waves. So we have to see here whether this formulation is stable or not. That is a very important topic. If you have any kind of nice equation, but if you want to calculate, but the solution blows up, then nobody would want to use this kind of methods. So that you have to show this one is stable. For this one, I show you the classical definition for stability. So if you have any kind of Cauchy problem means you have any first derivatives for vectorial solution, because you have the real, the power p. And this one is the time-dependent problem. And you have also any kind of partial derivatives in time and space. In space, you can also have any high-order partial derivatives in space. So we denote this one is a linear differential operator with the initial conditions. And we define the Cauchy problem is weakly stable if you have here these inequalities. For example, S is bigger than 0. But you can also have the strongly definition. Strongly, that means if we have S equals 0, right? S equals 0, that means we don't have any more these polynomials with t, right? So you have just bounded with the solution in weak sense in the Sobolev space. So there is a very famous theorem, Krauss-Lorenz, 1989. There is a necessary and sufficient condition for weak stability. That means you have here the partial differential operator, and if you put the Fourier transformation in space, I put here the Fourier transformation in time so that you have the frequency. But if you put the Fourier transformation in space, you obtain wave numbers. So that I have here the wave numbers, and then you calculate the real part of the eigenvalues that is bounded with the constant values. For example, C is bigger than 0, or C equals 0, then it corresponds to the weak stability. So for strong stability, that must be complete. Complete means each eigenvectors are independent. So that is a main theorem for stability. So I showed also, I submitted this research topic. The PML equation in two space dimension is strongly stable for damping parameters. In that case, it's theta 1 and theta 2. It corresponds to sigma. But the PML equation in 3D case is strongly stable and needs two layers. For example, you have a 3-coordinate system. Just at least the 2 is not, for example, in this case, 0, and otherwise it's weakly stable. That means our new equation is stable. So the at least is stable, so that you can use without any problem in numerical study. So there is also the overlapping area. So I study also the operator analysis. So that is very important for numerical scheme. So you can have any kind of numerical scheme. You don't show any stability, then it's just engineering work. But as a mathematician, I study also this kind of stabilities, so that we can believe our calculation is true. But you can see very often in the industry area, they calculate, you have the solution. So it works. But mathematically, we'll see it's not true. So you have to check with the stability and so on. Right.
Is there any physical example of the second case? That means at least among three, at least
yes. Yes. Yeah. For example, you can just test with the numerical calculations. For example, the problem is there are many kind of sources, various frequencies, but the stability in numerical scheme is also another sense. So you have to have sufficiently this condition, and the numerical, you can, for example, have any stable numerical scheme, so that you cannot always check it with the numeric, right?
But the second condition implies at each point,
yes.
if you discretize them,
yes, yes.
just you have a single dimensional.
Exactly. Yeah, yes, yes. I studied this one in the numerically. You can put some kind of point in the calculation domain. You can see how does, for example, how for example, the solution could be, for example, blow up or not. You can see just that. But otherwise, you can see that in the following picture. I will show the following picture, then you can see that. for example. So you can check it, for example, in 2D case, you have the PML solution and the reference solution. Reference solution means your calculation domain is too large, right? The wave propagates, and then the reflected waves come in the very late. So you can put, for example, from the time domain from 0 and 9. So I have here different coefficients. Then you can see that the numerical accuracy with the L2 error, so there is a Lebesgue integral in L2, is very small. You can see that is about 10 power minus 17. So that is very small. So in engineering area, the machine error is 10 power minus 16. That is also very nice. So nice. I calculated this one also in heterogeneous media. You could have also heterogeneous media. The real world problem is heterogeneous. This one and this one has different material coefficients. There is heterogeneous. So, for example, if you see that you have the initial condition, the wave propagates in the higher position in the y-axis, the wave propagates faster than the lower. Because, come back to the wave speed, you see that in the y-coordinate system, the wave speed is higher than lower one if you go the higher y, right? So wave propagates, and in the end, it's already the long time stable. So we can show that. So t equals 7, the wave propagates already. So we don't see here any kind of law. So no numerical scheme here verifies our also the analytical equations. 3D case here, you can see here any kind of source point in the middle of the domain, and here you can see that green one is the outside of the PML. So on the green one, you put the zero boundary condition, so there is a Dirichlet boundary condition. And then the wave propagates, and then you can see that the long time t equals 12, so we don't have any blowover, so the wave propagates very nicely. So our calculation verify also stable calculation in this case. So the second here, one is the numerical scheme. So you can have a stable analytical scheme, and you have to also have a numerical scheme which verifies stability, right? So I use usually 3 different methods: a finite difference method and finite elements method. You have new finite element method that is a discontinuous Galerkin. If you have a discontinuous Galerkin, you have in the end the block structures of the matrix. You have here equation, but if you want to calculate with the computer, you have to have any very big matrices. If you have a 3D domain and time, you have very huge matrices. There is a big problem, right? For example, calculation of earthquake, right? The wave propagates under the Earth. The wave propagates from the Korea to the US. If you calculate, for example, just a sequential calculation, it takes, for example, 1 year more, right? So that we have to put a very nice scheme which have a very fast calculation. So first I define here the edges of the finite element meshes. So for example, if you have any here, I show. Just imagine it. You have here just a box area. So we use any kind of numerical scheme. We say that it's a finite element schemes. Then you have to have any discrete points. So that means you have to decompose our computational domain with, for example, in this case, triangulars. For example, so we define here edges in our example. For example, HI and H boundary. So we say this one is edge in this triangular, but this edge is inside of computational domain, but this edge is on the boundary, so that we can decompose our edges two kinds of things. So interior error edges or boundary edges. But the problem is that you can also have discontinuous solution if you put, for example, any kind of jump operators, for example, in these edges, so that we define here with this operator. So that means you obtain some kind of differences of two solutions on the edges. Or you have the jump. With the solution, you can also calculate the average of the two solutions on the edge. So, but problem is on the boundary, you don't have any neighborhoods. So you put just these normal vectors to outside, and also you put this one. And interesting is here just a mesh size. So if you have this triangular, your mesh, for example, size defined with this in radius. For example, this one is h. So each triangulars have, in this case, you can see that different size of mesh. But so that we define this mesh size in our case with the edges. So for example, you can put these edges. Then you have to see that this edge is also, it belongs to these elements and these elements, so that you have to compare. So I write the minimum, for example, and this one. So if you put this formulation, for example, that is just a weak formulation with this operator, that is L is the time derivatives, and then you find here right-hand side F tilde and G, and then you put just a rigorous scheme for weak formulation, and then in the end here it looks like complicated, but that is just an integral formulation for our equations. So I use this one because, as I said, you obtain block structures of the matrix, then you can calculate very fast, so without any long calculation. The second one is electromagnetic wave propagation, so that that is analog. So you can also put PML layers for Maxwell equations. Here I show just the electric solution in Maxwell equations. Also, the blue one is the given Maxwell equations. And then you put here the auxiliary variables, phi, j, and psi. And j is 3 different variables. So it defines with this one. So I calculate here numerical example with photonic crystals in nanoscience. In nanoscience, you have here the periodic structures. You can take this one, for example, with the metamaterial. It's a very famous metamaterial. It's from Opal. Then you can have a very nice periodic structures with the periodic dielectric coefficients that correspond to this one. That means here you have any way, so dielectric coefficients is 0. Otherwise, you have just periodic. So you have any kind of source here, left-hand side, then the wave propagates to here, and then you have a nice bending problems. That is very nice because you can control your light if you want. So you can control. So previously, for example, the human beings, they thought you cannot control the waves. For example, electromagnetic waves. For example, you can see light. That is also electromagnetic waves. But now you have to control this one because if you see the semiconductor, the transmission the rate is very low. For example, between 20 and 30%. So you lose your energy. The calculation time in the semiconductor is very slow. We have to here have nice, efficient numerical scheme for this one. So I calculate this one based on my the new PML equations. Then it works also very fine without any problems. So I have also software. I use a software package that engineer can use without any problem. So that is purpose. I want to also collaborate with engineers. Then they can use our software, and then we verify also the stability. So right, there are many commercial softwares which don't show stability. There is big problems. So problem is in nanoscience, there are many kind of laboratory experiments. The problem is the instrument is too expensive. So if you have a good calculation, you can calculate very nice simulation. Then you can compare your laboratory results. Then you say, oh, our calculation it works very nice. So then you can have very expensive new nano materials. You can sell it and so on, right? There is idea for this in this area. There is also main topic.
So you can make lights.
Exactly.
Semiconductor.
Exactly. So we had the industrial cooperation in Berlin, 2004 and 2005. We had the industrial partner, the Siemens. It's a very big German electronic company. Then we also we gave any kind of software computations. So I think if you have this one, then in 20 years, you can have people-like monitors. You can. That is the idea. If you have this one, you can build very easily or nicely some kind of displays or semiconductors also. Okay. The last example in the electrodynamic wave propagation. So the solution of U is the displacement. For example, it happens also if you have any semiconductor, you have any heating, the material, the parts, it could have any displacement. You have to also this kind of equation. That means it is multi-physics, right? You have to use Lexer equations and elastic equations and so on. So I made also the PML equations also that is in my also the PhD series. So we have finished this one also. We verify also very nice numerical schemes. So I tested here with different material coefficients. So I show you just here. So wave source is here, the wave propagates outside. Here we have the PML layers. You can see it here, and the wave propagates stays long time. You don't have any instability in this problem. Second material, the wave propagates and so on. Also, you don't have any problem. So that is the one. So the third part is multiple scattering. In the real world problem, we have many scatterers. For example, if I use mobile phone, I'm also one scatterer, or you also the different scatterers. The wave propagates here and here. There are many interactions. You have to calculate also that. For example, that you have two scatterers. Our calculation domain is that. For example, if our distance is too large, we have to have a very huge the computational domain. So the idea is that we give any surrounded layers. Here you have two scatterers, so that you calculate just here and here. So your computational domain in this case are reduced, right? The problem is that you have also, if you calculate this one, the problem is the wave propagates from here and to here and here. So you have, during your calculation, you have always the interactive waves, right? You have to also capture this one. So, right. Okay, so we have to have also here new type of boundary conditions. In PML layers, we absorbed the waves. The problem is if the waves absorbed in the PML layer, we don't know exactly in another direction, right? But if you use another boundary conditions, you can perhaps capture these outgoing solutions. That is the idea. For this one, there is a classical formulation, that is far-field evaluation, Kirchhoff formula. I think over 90% in the world they use these integral equations. Also in inverse problem also, that is integral equations. The problem is that if you have the solution u, as I wrote here, in spherical domain, you have r, theta, and phi, and time. For example, you can imagine it, it's 3D sphere. Then you have the integrals. For example, if you want to calculate this one, you have to integral in 4 dimensions. So that means your calculation time is too large. So we have to avoid this one. So I have the new idea. Thomas Hagstrom and Hariharan, they followed, for example, the following scheme. So for example, you have any kind of scatterers. In the PML layers, you give the additional layers surrounding this one, right? But Thomas Hagstrom and Hariharan, 1998, they don't use any observing layer. Just you put any kind of data points. In this data point, you calculate with the operator B the new auxiliary variables. And then you calculate based on this new auxiliary variable sequentially, for example, J1 and 2 and so on until P. In general, if you P infinite, then you obtain the exact representation of our scheme. The problem is if you calculate with the computer, you cannot put with the infinite, right? You have to truncate these solutions. And then the numerical schemes, with this one, you can find the auxiliary variables has with the radius. That means if you have the large computational domain, that means you can find in spherical domain the radius. The radius is very large. Then Wj plus 1 is quite small. That means, right? Also, if you put the higher number of auxiliary variables, then you can see that higher number of j, then the Wj is also very small. That means you have two options. You can enlarge the radius, or you can increase the number of auxiliary variables. So I show you the numerical test. So I put here just these data points in the numerical scheme. Then I compare with the exact solution in the second layer. So the idea is we want to see here any kind of spurious solutions. So we see here we don't have any spurious solutions. The wave propagates without any problems. So the wave propagates in the time and then goes and then comes again, right? So in this case, I used the heterogeneous wave speed. Okay, I show you a very nice, efficient representation formula. In my PhD series, I made a new type of representation formula. For example, you can imagine it computational domain omega, and psi 1 and psi 2 is that. As a Professor So and I is here. And then for example, you send the labels and then reflections. For example, I can move my position, but my position is local, also local in time. That means with this one, I showed you the auxiliary variables, and then you have any kind of position in space and time, then you can calculate based on these auxiliary variables locally. That means you don't need to calculate integral equations, just you put the auxiliary variables based on the previous solution. You can see that it's a previous solution. The way we propagate, for example, from here and then, you have any duration because of the distance. Distance is, for example, r minus big R. Also, this distance you can control with the wave speed, right? For example, wave speed is very large, then the wave propagates very fast, right? So it is the idea. So that we store the best values of the auxiliary functions on the boundary, and they evaluate solution everywhere outside omega through this exact representation. So that if you use this one, you don't need any supercomputer. So that is the idea.
Is it for two scatters case?
No. It's you can have any arbitrary number of the scatters. For example, you can have also 100 scatterers and so on. So that is the idea. So that you can use this one very efficiently in molecular dynamics. For example, if you're having some kind of materials, you have a huge number of molecules, so you use also this one. Right? It's very efficient formulations. So I show you just one case. For example, you have a two domain, omega 1, omega 2, then the wave propagates, for example, from omega 1 with the red one, and then the reach, and then the wave propagates from omega 2 and omega 1, the blue one, and then the wave propagates interactively, right? So that corresponds to. So for this calculation, you need any new boundary conditions. So I have here outgoing solution from omega 1 and incoming solution, for example, omega 2, omega 1, incoming solution. Then on the boundary, you have the total solution, omega B1, on the surface, on the boundary case, in the B1 and B2. And then you build here this new boundary apparatus, and then you put it. So the idea is that we use the representation formula. For example, you want to calculate P2 and P3, then you need just 1 point. So you can have here P0. For example, you want to have any numerical solution in the position P4, then you calculate just this one. Everything is locally. The problem is that you can have also some kind of position. For example, this one is okay. You can have here good layers. It corresponds to these layers. The problem is the red one. So red one is not on this line. So, but you can calculate interpolation. So based on this local interpolation, also that is also a new one in my PhD series. Based on the Arkema local spline interpolation, I calculate this new local scheme. In general, in classical case, you have to calculate big matrix structures. It takes a long time, but you have just a finite number of the interpolation numbers. So perhaps you can see it much better with my computation. So you send incident wave, you have scatterers, and then the wave are reflected, this blue one. Then wave propagates to left-hand side.
Does the non-reflecting means observing?
Exactly, yeah.
Which one is the common or what is the non-reflecting?
No, that is not common. So the problem is that in this case, you don't have any just observing conditions, but also you have to also propagating solutions. In classical boundary condition, you cannot just you can just calculate observing solution, but you cannot calculate propagating solution. But in my formulation, I calculate both cases: propagated solution and observed solutions. So I don't have also any stability. The wave propagates, and then the energy are them, so that you can see that amplitude are always smaller and smaller. So I have to have also the numerical accuracy of the evaluation formula. So I have also some point source. Here is my calculation domain, and then I build here the auxiliary variables for boundary condition, and then I compare with my solution with the representation formula and with the exact solutions. So I don't have any reflections here. And then you can control the number of auxiliary variables. If you have a high number of P, then it approximates to exact solutions. So there is a radius. I put here some position based on this radius. For example, you can truncate the coordinate, and then you can just see that with the here the varying time, right? So you can also show with the mesh size. For example, the mesh size, that means you have to also have a huge number of discrete points. But you can have also a large number. But the problem is that if you have low number of auxiliary variables, then numerical accuracy is very poor. For example, you cannot have always the good approximation. But if you have the high number of auxiliary variables, you can have, for example, second order scheme in our case. So we don't have any as a poor solution. So our calculation, it corresponds to good numerical accuracy. So concluding remarks. So our calculation is based on the straightforward and cheap implementation. In the second order PML formulation in wave equation or Maxwell or elastic-dynamic equations. Also, we have effective far-field simulation with locally high-order representation formula without integral equation. And third one is easily coupled with the finite difference and finite elements. And you can also have nonlinear sources or arbitrarily complicated obstacles inside omega. So recently I also calculated and wrote some kind of works with my colleague in India in France. So convective wave equation in aerodynamics and poroelastic things for the earthquake also. So first, so that is my talk until now. So do you have any questions? Yes, you have.